A span of vectors is the collection of all linear combinations of the vectors. We denote this as span v1, v2 up to vk. What this means is any vector u in the span can be written as u equals c1 v1 plus c2 v2 plus ck vk for some scalars c1 up to ck. Let's talk about cookies again. You can make a wide variety of cookies using a combination of butter, white sugar, brown sugar, water, eggs, vanilla, baking soda, salt, flour, chocolate chips, and oatmeal. For example, you can make sugar cookies, butter cookies, chocolate chip cookies, oatmeal cookies, chocolate chip oatmeal cookies, shortbread cookies. Hold on, was that a cake? Wait a second. What's happening? All right. Because we're discussing a span, we must consider all combinations of these ingredients. That can include cake, oatmeal, a pile of flour, a shot glass of salt and baking soda, and of course a vanilla egg smoothie. Eventually, we'll discuss how to determine what a span is. The words are the column space of a matrix. For now, we'll ask questions like, is this in the span? For example, could we make peanut butter cookies using our ingredients? No, we're missing peanut butter, or peanuts if we just wanted to make peanut butter. How about numbers? Is the vector 2, 4, 1 in the span of the vectors 2, 1, 2 and 0, 3, minus 1? Remember, the span is the linear combination of the vectors. So what this is really saying is 2, 4, 1 a linear combination of 2, 1, 2 and 0, 3, minus 1? Or are there constants c1 and c2 so that 2, 4, 1 equals c1 times 2, 1, 2 plus c2 times 0, 3, 1? And we've solved things like this. It's a system of linear equations. We could go through the whole process again. Or we could observe that c1 equals c2 equals 1. Since we found a c1 and c2, we can conclude that 2, 4, 1 is in the span of 2, 1, 2 and 0, 3, minus 1. But what does a span look like? Let's consider two vectors, u equals 1, 1 and v equals minus 1, 1. We'll need a two-dimensional axis since these are two-dimensional. Label this as span of u and v. We'll represent vectors by a point. So u is here and v is here. We start taking linear combinations of u and v. U plus v is 0, 2, so that's in the span. 2u plus 0v is 2, 2, mark that point. In fact, any scalar multiple of u is in the span. I'll represent that as a dotted line. The same can be said for v. U minus v and v minus u are both in the span. Let's pick a point completely at random, say 1, 3. Is this vector in the span? Yes, it is. 1, 3 is equal to 2u plus v. In fact, any point we pick will be in the span. Try a few points for yourself, you'll see. Therefore, the span of u and v is equal to R2. Is it a coincidence that it took two two-dimensional vectors to span a space that was two-dimensional?